G'day guys, and welcome to our lesson on electric power made easy, in which we learn when to apply these power formulae to find the power dissipating in things like light globes, electric motors, and small, alarms and things like that. The number one thing I want to emphasize is when you're using these formulas is you use what you have. So if you have the voltage and the resistance over a component, unless you're specifically asked to, don't go and find the current so you can use this formula up here. Just use this one down here. And you can often find the power dissipating in certain components without necessarily knowing the resistance, the current, and the voltage. You only really need 2 out of 3. So let's draw a circuit here. First resistor here, second resistor here, and third resistor here. If we use a 10 volt power supply here, the first resistor is 4 ohms, the second one is 6 ohms, and the third one is 10 ohms. Let's figure out the power being dissipated in these 3 components. So first of all, let's figure this out. We have the resistance for this component, but we don't have the current and we don't have the voltage across it. We don't have the current or the voltage across this one or this one here. So the first thing we're going to do is figure out the current going through each of these 3. Because it's in the series, the current's going to be the same. Now we look at this from the perspective of the battery. The battery just feels a big resistance on itself. It doesn't know what's going on down here, whether it's a number of resistors or a single one. And this resistor here is RT. And we found out before the formula for the total resistance in a series is R1 plus R2 plus R3 plus however many you have. In this case, R1 equals 4, R2 equals 6, R3 equals 10. So 4 plus 6 plus 10. That's 20 ohms. So now we apply Ohm's law. I should put that in up here. V equals IR. 10 volts V total equals I times 20 ohms, which is R total. So 10 over 20 equals I equals 0.5 amps. We've got 0.5 amps going through here, here, and by extension, all these 3. So now we know the current going through these 3. Which power formula are we going to use? Well, of course we're going to use the one that shows current and resistance. P for this one here is equal to I squared R, which was 0.5 squared times 4, or 1 on 4 times 4, 1 watt. The power for this one here is equal to I squared R, which is equal to 0.5 squared, that's 1 on 4 times 6, which is equal to 1.5 watts. The power for this resistor here, I squared R, 1 on 4 times 10, 2.5 watts. And if you add up these 3 powers, 1 plus 1.5 is 2.5, 2.5 plus 2.5 is 5, so we have the total power is 5 watts from adding up these 2. We can also recognize, hey, if there is 10 volts here and there's 0.5 amps flowing through it, then power is also equal to VI, or 5 watts. So the power that's being, we'll say, pumped out by this battery is the same power that's being used up on these resistors. The total energy of the universe is conserved. It actually gets easier with parallel circuits. We'll have a look at an example of a parallel circuit. 10 volt power source, 3 resistors, all in parallel. we have a 4 ohm here, a 6 ohm here, and a 10 ohm here. We said in series, in our previous lesson, that the voltage across this resistor must be the same as these other components. And it also must be the same as the battery in this case, because there's nothing else taking up voltage here. So this is 10 volts, 10 volts, 10 volts. We don't even need to find the current, because there is a power formula involving voltage and resistance. It's here. The power being dissipated across this resistor is V squared on R. V is 10, so that's 10 squared on 4, 100 on 4, 25 watts. The power being dissipated across this one is equal to V squared on R, so 100 on 6. I have that coming to 16.7 watts. And the power for this resistor down here is 100 on 10, or 10 watts. And we'll do an interesting little exercise here. If we add up the power being dissipated across these three components, we have 25 plus 16.7 plus 10. That comes to 51.7. And we could actually figure out the current here by applying this power formula there. The power total is equal to the voltage times the current. 51.7 is equal to 10 times I. So 51.7 over 10 is equal to 5.17 amps. That is the total current that is passing through this point of the circuit. So we can solve for current actually using our power formulae. Finally, let's check out a combination circuit. We drew this one before in our previous lesson. All in one colour to save time. So we have 4, 6, 10. Those are our resistances. And let's figure out the power at each of these positions. Well, the total resistance of this circuit is going to be this resistance here plus the total resistance of this parallel section. And the total resistance of this parallel section is equal to 1 on 4 plus 1 on 6, the power of negative 1, 2.4 ohms. And the total resistance of this part here is equal to 10 ohms. So we can model this circuit as just two resistors in series. I had a bad feeling before. I may have mentioned that in series the voltage across all the components is the same. That's not true. In series, the current through each component is the same. It's in parallel that the voltage across each component is the same. I have a bad feeling I misspoke before. 2.4 ohms here, 10 ohms here, and this can be further modelled as a single 12.4 ohm resistor. If it really does have 12.4 ohms of total resistance, that's the RT for the entire circuit. If we were using a 10 volt power source here, V on RT equals I, 10 on 12.4, that's 0.81. We know there's 0.81 amps going through this whole circuit. Here, 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 and then it must split off into two lesser currents there. Since we now know I equals 0.81, and we know the resistance here, we can apply the I squared R rule. That's 0.81 squared times 10, and I have that coming to 6.56 watts. Over here, I still don't know the power across either of these components. I think the best thing to do is to calculate the voltage across these components. If we modeled the circuit like this, we'd find 2.4 ohms here and 0.81 amps flowing through. So the voltage across this section of the circuit, the voltage drop, is IR, 0.81 times 2.4, which is 1.94 volts. And that must be across both these. So since we now know resistance and voltage, we can apply this formula here. 1.94 squared divided by 4 is equal to 0.94 watts, and power down here is equal to I squared R, 0.81 squared times, V squared on R, which is equal to 1.94 squared on 6. I have that coming to 0.627, so 0.63 watts. Hopefully that has shown you how to calculate the power given off by each individual component. And the one tip to take away is that if you want to check your answers, add up the power from each component. So here it was 0.94, 0.63, 6.56. That comes to a total of 8.13 watts. Then I can go back here and say I did find that there was 0.81 amps flowing through here with 10 volts. So P again is equal to VI. That's 10 times 0.81, 8.1 watts. So the power I calculated from the macroscopic view, the bird's eye view of my circuit, once I've modeled it down to a very simple circuit, is the same as when I added up all the power of all the individual components. The first law of thermodynamics, the energy of the universe is always conserved.